Hi there. Now here I've got a mixed exercise that you might like to try on Pythagoras' theorem and trigonometry, where I've got 6 questions here and you've got to find either the length of a side x or the angle theta for these right angle triangles. So if you'd like to have a go at these, just give you a moment as usual to pause the video, and when you come back I'll display all the answers, the numerical answers, to one decimal place. Then after that I'll take you slowly through the workings for each question. Okay, welcome back then if you had a go. So here are the numerical solutions then to all the questions given to one decimal place. Well done if you got them all right. But what I'm going to do now is just take you slowly through each question, and obviously you might want to fast forward just to check out any particular question. Okay, so let's just remove these answers and we'll start with number 1 then. Now with number 1, this is a typical Pythagoras' theorem question where we've got 2 sides of a right angle triangle and we need to work out the missing side. And in this question we're asked to find a shorter side, because remember the hypotenuse is the longest side, the side that's opposite the right angle. So using Pythagoras' theorem, should be familiar with this. If not, do check out my earlier video tutorials. We've got the hypotenuse squared, that's the side opposite the right angle, is equal to the sum of the squares of the other 2 shorter sides. So that's x squared plus 3.9 squared. Well, obviously you could write 3.9 squared plus x squared. Now you just take away 3.9 squared from both sides and you therefore have x squared equals 5 squared minus 3.9 squared. And then if you work this out on your calculator, you'll end up with x squared equaling 9.79. And then you take the square root to both sides to get x. X will equal the square root of 9.79. It won't be plus or minus here because the length of a side can only be positive. Okay, so what does this equal? Well, it equals 3.12 and so on. It's measured in centimetres. We've got to give the answer to one decimal place, so it's going to be 3.1 centimetres to one decimal place, 1 dp there for short. Okay, so that's number 1 then. So we'll move on to the second one, okay, and in number 2, here we've got to find the angle theta. And so we need to think of the 2 sides that we've got here. In relation to the angle theta, this is the adjacent side, and this one here, opposite the right angle, is the hypotenuse. So the trigonometric ratio that connects the adjacent and hypotenuse is the cosine ratio. Cosine of an angle equals adjacent over hypotenuse. So therefore for this one we would have the cosine of the angle is theta, equals the adjacent side, 3.1, divided by the hypotenuse, 4.8. And if you work this out on your calculator, you'll find you'll get 0.6458 and so on. And then we need to take the inverse cosine to both sides and we end up with theta equals the inverse cosine of that decimal, 0.6458 and so on. Now make sure your calculator is in degrees mode, and assuming it is, you should find you get 49.77 and so on. And we're measuring this in degrees, so it's 49 point, and it's to one decimal place, so it's going to be 49.8 degrees to one decimal place. Okay, so that's number 2, and we'll just move on then to number 3. Now in number 3, we're being asked to find the length of a side, and for this question then it's going to be using trigonometry because we're given an angle here. It's not a Pythagoras type question. So we've got the opposite side to the 50 degrees, so label that O, and X is the side opposite the right angle, so that's the hypotenuse. So that means we need to use the sine ratio here. Remember, sine of an angle equals the opposite side over the hypotenuse. So with this one then, we have got the sine of the angle, sine of 50 degrees, equals the opposite side, 6.2, divided by the hypotenuse x. And then we multiply both sides by the denominator here, x, when you get the unknown in the denominator. So we end up with, therefore, x times the sine of 50 degrees equals 6.2. And then to get x now, we divide both sides by the sine of 50 degrees. And so therefore x equals 6.2 divided by the sine of 50 degrees. And with this one, again, make sure your calculator is in degrees mode. And you should find you end up with 8.093 and so on. And x is measured in kilometers here, being a length, and to 1 decimal place then, this is going to be 8.1 kilometers to 1 decimal place. Okay, so that's question number 3 done. So we're moving on now to question 4. So
our brain can potentially memorize 2.5 petabytes of information, which is roughly the equivalent of 3 million hours of YouTube videos. In order to use some of that staggering capacity a little more effectively when you learn, here are some tips that are based on widely accepted research by neuroscientists and learning experts. Spaced repetition. To maximize your learning, study short but often. Neuroscientists proved that synapses, the million billion connectors in your brain that make you remember and understand stuff, grow mainly at night when you were asleep. This means that it is more productive to study regularly with sleeping breaks in between. Try it. Practice something for 15 minutes every day and you'll be surprised by your progress within just weeks. Find your own style. While listening to the history teacher, Tom scribbles images and Jane finishes 1 kilo of nuts. Some enjoy watching videos over reading books, others study with friends, and some like sitting in silence among a million books. Everybody is different. Good night's sleep. Sleep and dreams are vital to processing and storing new information. A Harvard study showed that students who had a good night's sleep remembered their study materials 35% better than those who studied in the morning to take a test in the evening. Focus. If you tend to procrastinate, which means that you tend to switch from doing something hard like studying maths to something easy like browsing the web, protect yourself from distraction. One way of doing this is to shut down your mobile phone or go to a quiet place like a library. Pomodoro technique. Set a timer to 25 minutes when you focus entirely on your studies. When the timer rings, relax for 5 minutes. If you want to continue, just set the timer again. The small breaks in between are relaxing and motivating to keep going. Hard stuff first. Do the things that are difficult first, because if you are like most people, you have the strongest willpower in the morning. Once you are done with the hard stuff, you will feel better for the rest of the day and probably more motivated to get other things done. Exercise, meditate, and converse. There are few activities proven to grow your brain. However, physical exercise, regular meditation, and good conversations apparently do exactly that. They lead to the creation of new neurons inside your brain and therefore grow its potential. Go places. You can create deeper memories of a subject by learning in a richer environment that offers more visual clues. In an experiment, 2 groups of students had to remember random words. One group changed the classroom while studying, the other didn't. The group that studied in two different rooms, one was small and windowless, the other big and bright, was 40% more likely to recall the words later. Take fun seriously. Whatever it is, find a fun way to practice. Modern learning science believes that positive emotions are very important for increasing your learning potential. So do yourself a favor and have a good time. Space your studies. In order to remember things for a longer time, repeat the material in spaced intervals. Facts or vocabularies, for example, are best learned if you review them the first time 1 to 2 days after the initial study, and then again after 1 week and after 1 month. 30% read, 70% recite. If you have 1 hour to learn to recite a poem or prepare for a speech, spend 20 minutes of the time on studying the text and 40 minutes on practicing to recite. This ratio usually leads to the best results. In the case of an emergency, put a glass of water next to you. Take a sip whenever you lose it. Instant self-test. After you study, finish up with a quick quiz. Immediate recall in the form of a test or a short summary on what you've just learned can increase retention by as much as 30%. Because it's much harder for your brain to reflect than to read, that extra effort creates deeper traces in your memory. Don't force it. Motivation is like hunger. You cannot force yourself to be motivated, just like you can't tell someone else to be hungry. So if you are not hungry right now, don't worry. Take a break and do something else.
With question number 4, again we've got to find out the length of a side given an angle and another side. So this is going to be trigonometry again. So we've got the opposite side to the 25 degrees here, and this side is the adjacent side. So labelling it up in the usual way, we now look at the ratio that connects opposite and adjacent, and it's the tangent ratio. So we have the tangent of the angle, tan of 25 degrees, equals the opposite side, which is x, over the adjacent 2.3. So with this one, we just need to multiply both sides by 2.3, and that will give us the value of x. X equals 2.3 times the tangent or tan of 25 degrees. And make sure your calculator is in degrees mode, and you should find you get x equals 1.072 and so on. And the units for this are millimeters, so to 1 decimal place this is going to be 1.1 millimeters then to 1 decimal place. Okay, so that's number 4. Moving on again, we've got now question 5. And with 5, what have we got here? We've got 2 sides and we've got to find the third side. So when you've got any 2 sides and you've got to work out another side, it's Pythagoras' theorem. So what we have here is 2 of the shorter sides given, and we've got to work out the hypotenuse. So therefore this one is just going to be the hypotenuse squared, that's x squared, equals the sum of the squares of the other 2 shorter sides. So that's 3 squared plus 2.8 squared. So we don't have to rearrange this, we could just work this straight out on the calculator, and if you do, you end up with 16.84. Square root both sides, and you therefore end up with x equals the square root then of 16.84. So we don't need plus or minus because it's a length, okay, and only lengths can be positive. Square root this and you find you get 4.103 and so on. And giving this to 1 decimal place, we've got 4.1, and the units are centimetres. So it's 4.1 centimetres to 1 decimal place, 1 dp. Okay, well, we're on to the last one now. And the last one, well, this is just going to be a little longer because it involves several stages here. In order to find out x in this one, we need to, first of all, work from this triangle here. And we need to get the hypotenuse. So it's going to involve trigonometry. And once we've got the hypotenuse here, we can use Pythagoras' theorem on this triangle because we'll know two of the sides. Okay, so let's start with this triangle. And for trigonometry, we want to find the hypotenuse. So we'll just label that h there. And we're given the adjacent side to the 23 degrees. So the trigonometric ratio that would connect the adjacent hypotenuse is the cosine ratio. So we'd have the cosine then of the angle, 23 degrees, equals the adjacent side, 5.8, over the hypotenuse. Okay, so I'll call that h at this stage. Okay, h. And then to get h, I'm going to times both sides by h because it's in the denominator here. And so therefore I've got h times the cosine of 23 degrees just equals the 5.8. Now I can divide both sides by the cosine of 23 degrees and that gives me h equals 5.8 divided by the cosine of 23 degrees. And if you do that, you'll end up with this equaling 6.300 and so on. And that's measured in meters. Now I'm not going to round up here, and I'm carried this on beyond 1 decimal place. I don't want to have any rounding errors, okay? So I could either store this in my calculator or just use this number later on. It's not going to change the accuracy. Not to 1 decimal place, that is, anyway. So now that I know this length here, okay, we can now use Pythagoras' theorem over this triangle, where we've got the hypotenuse and we're after a shorter side. So in that case, I've got that the hypotenuse squared, so that's going to be 6.300 and so on squared, is going to equal the sum of the squares of the other two sides. So that's x squared plus the 4.1 squared. So rearranging this for x squared, if I take off 4.1 squared from both sides, we've got 6.300 and so on, all squared minus the 4.1 squared. And working this out, you should find you get 22.891 and so on. And so just need to square root both sides, so therefore x equals the square root then of all of 22.891 and so on. And if you do that, you end up with 4.784 and so on. And rounding this then to 1 decimal place, you're going to get 4.8. 4.8 meters to 1 decimal place. Okay.
What I want to do in this video is talk about the difference between vectors and scalars. And they might sound like very complicated ideas, but we'll see over the course of the videos that they're actually very simple ideas. So first I'll give you a little bit of a definition, and then I'll give you a bunch of examples. And I think the examples will make things super clear. Hopefully they'll make things super clear. A vector is something that has a magnitude, and or you could kind of view that as a size, and it has a direction. So and it has a direction. And it has a direction. A scalar only has a magnitude or size. And if that doesn't make sense to you, it will hopefully make sense to you in a second when I show you an example. For example, let's say that I have let's say that that's the ground right there. Let me do the ground in a more appropriate ground-like color. So this is green right over here. And let's say that I pick and I have a brick here. I have a brick on the ground. And I pick up that brick, and I move it over to this place right over here. So I move the brick right over there. And then I take a ruler out, and I say, wow, I've moved the brick. I have moved the brick 5 meters. I have moved the brick 5 meters. So my question to you is, my measurement of 5 meters, is it a vector or a scalar? Well, if I just tell you 5 meters, you just know the size of the movement. You just know the magnitude of the movement. So if someone were to just say 5 meters, this is a scalar quantity. Scalar quantity. And when we're referring to moving something, or how much something has, I guess, changed its position, and I don't give you the direction, we're talking about distance. And I'm assuming you've heard the word distance. How far of a distance has something traveled? So this is distance. So we could say that this block, or this brick, because of my picking it up and moving it, has moved a distance of 5 meters. But if I didn't show you this picture here, and someone just told you that it moved a distance of 5 meters, you wouldn't know if it moved to the right 5 meters. You wouldn't know if it moved to the left 5 meters, if it moved up or down or in or out, or you don't know what direction it moved 5 meters. You just know it moved 5 meters. If you want to specify that, so we could say that this brick right over here, that it moved 5 meters to the 5 meters to the left. 5 meters to the left. Now we have specified a magnitude right over there. So that is a magnitude. And we have specified a direction to the left. So you now explicitly know that it went 5 meters to the, oh, sorry, it should be 5 meters to the right. Let me change that. So 5 meters to the, that's why the direction, to the right is what it got moved. It started here, it went 5 meters to the right. So once again, the magnitude is 5 meters, and the direction is to the right. So what I've just described to you right here is a vector quantity. So this, all of this business right over here, this is a vector. And when you talk about the movement, the change in position, and you give its direction, the vector version of distance, I guess you could call it, is displacement. So this right here is displacement. Displacement. So the correct thing to say, you would say that this brick has been displaced 5 meters to the right, or it has been moved a distance of 5 meters. Distance is a scalar quantity. I didn't tell you what direction we moved it in. Displacement is a vector quantity. We told you that it is to the right. Now let's explore this if we talk about the actual, well, we'll talk about the speed or velocity of something. So let's say that that this 5 meters was traveled, and let's say that the change in time, and when let me just, because you're probably not familiar with what that means. So let's say that the change in time right here, change in time, when I moved this block 5 meters, let's say that it was, I don't know, let's say that the change in time was 2 seconds. So maybe right when the block started moving, maybe on my stopwatch it said 0, and then on my stopwatch when it stopped moving, it said, or when it got to this position, I should say, when it left from this position, my stopwatch said 0. When it got to this position, my stopwatch said 2 seconds. So the change in time, or the duration we're dealing with, is 2 seconds. And this is, for all we know, time only goes in the positive direction. So you could assume that it's, well, you could pick that as a vector or a scalar quantity, I guess, because there's only one direction for time, as far as we know, or at least in what we're going to deal with for the simple physics. So what's a measure of how fast this thing moved? So how fast did this thing move? So we could say it moved 5 meters in 2 seconds. So let me write this down. So it moved 5 meters. It moved 5 meters per 2 seconds. Per 2 seconds. Or we could write this as 5 halves of a meter per second. Or 5 divided by 2 is what? 5 divided by 2 is 2.5 meters per second. meters per second. Meters per second. This right here is just the 5 divided by 2. Let me make that clear. That right there is just the 5 divided by the 2. So my question to you, this 2.5 meters per second tells you how far it traveled in a certain amount of time. Is this a vector or a scalar quantity? It is telling you how fast it went, but is it giving you just a size of this of how fast it went, or is it also giving you direction? Well, I don't see any direction here. So this is a scalar quantity. And the scalar quantity for how fast something is going, is speed. So we could say that the speed of the brick is 2.5 meters per second. Now, if we do the same calculation, we say it went if we say it went 5 meters, I'll just write m for meters, 5 meters to the right in 2 seconds, then what do we get? We get 2.5, once again, 2.5 meters per second. I'll just abbreviate them as meters per second to the right. To the right. So is this a vector or a scalar quantity? I'm telling you the magnitude of the speed. That's right here. This is the magnitude, 2.5 meters per second. And I'm also telling you the direction, to the right. So this is a vector quantity. This is a vector quantity. And when you specify both the speed and the direction, so the 2.5 meters per second is a scalar, and the direction, you are talking about velocity. You are talking about velocity. So easy way to think about it, if you're thinking about change in position and you specify the direction of the change in position, you're talking about displacement. If you're not talking about the direction, you want the scalar version, you're talking about distance. If you're talking about how fast something is going and you give the direction that it's going in, you're talking about velocity. If you don't give the direction, you are talking about speed. Hopefully that helps you a little bit. In the next video, we're going to start working with these a little bit to start solving some basic questions about how fast something is going, or how far it might travel, or how long it might take it to get someplace.